Yeah, thank you so much for having me here. It's so exciting to be in India, and I look forward to see people. Yeah,
attending, so
and
they may ask you questions.
yes, no, absolutely. Oh, and that's where, no, absolutely, very good. So I'll tell you a story about an attractor mechanism that I've adapted to modern stuff in nAdS2. My incredibly witty title seems to entirely go unnoticed.
Oh, I noticed
Get misspelled everywhere, but
I noticed that right away.
This is my fault. I told them it's clearly a typo.
So all right. So let me start with just a broad introduction. Why are we interested in nAdS2? Well, extremal black holes, they're interesting, they're important because they are the class of black holes that have the smallest possible mass in a given superselection sector, so we can think about them as ground states. The spherically symmetric, asymptotically flat black holes in 4 dimensions, which are the ones I'm going to focus on, they have a near horizon geometry nAdS2 cross S2, so this is where you get your nAdS2 from. Think about it as the RT plane of a spherically symmetric black hole. In fact, a much more general statement, theorems, that all extremal black holes have an nAdS2 factor, including rotating black holes of various kinds, but I won't go there. I will just say that nAdS2 are very common, and that's why we're interested in nAdS2 quantum gravity as a toy model.
All regular extremal black holes.
Ah, yes.
I
think it's charging.
Because there's this claim about black holes in nAdS5, which you may have seen by Santos and collaborators.
Yeah.
New supersymmetric black holes.
Right. That's right.
And they have a horizon.
They have a horizon that goes irregular and develops a singularity, the exact extremal limit that is regular.
Yeah, no, they're very funny. I haven't. I printed them out. If it'd been a longer plane ride, I would have read the papers too. But because there's an interesting story there, I think.
The fact that you can have, as you know, singularities which are null in extremal systems, that's an old story. I don't know if that's what they're finding. But
is this with finite entropy? No. Yes,
No.
this has finite entropy
Yeah.
as singular.
oh,
Yeah. So it's a regular limit of finite entropy. I mean, it's a limit of regular finite entropy solutions, and so the entropy should be reliable.
No, look, the nAdS5 look, they're funny. This is, there's a big universe of things one could look at, and here I will look at the most simplest ones, and it's interesting to generalize to various other contexts, and and no doubt, various twiddles that come along. But the upshot is we are interested in nAdS-CFT correspondence, even for d equal to 1. Now, it's confusing with nAdS2 CFT1 correspondence for a variety of reasons. In particular, if you put finite energy excitations inside your nAdS2, you will realize that the back reaction on nAdS2 is such that you no longer have an nAdS2. So in that way, you've ended up in a little bit of a conundrum here. There are many unrelated unpleasantries. So the upshot is that if you say, why don't I just go and look in my d equal 1 chapter of my nAdS-CFT review, you will find that there is no such chapter. Or if you do find that there's a chapter, it's a really confusing chapter because the author probably didn't understand it. So yeah, I did check, it's fine. So this conundrum has been with us for a long time. In the last 3 years or so, there has been a new version of it, a new approach to this problem, which is basically entirely circumventing it. It's saying, well, look, who really wanted nAdS2 CFT1 in the first place? Why don't we go instead and study nearly nAdS2? So basically saying, look, we put energy in, we deform the boundary conditions. Well, that's tough. Let's say that if that's what we have to do, that's what we have to do. So it's no longer nAdS2, it's nearly nAdS2. And as a consequence, its dual is no longer CFT1, it's a nearly CFT1. The conformal symmetry, in other words, is broken. It's broken explicitly by these boundary conditions, by the fact that we actually do deform our boundary condition at infinity a little bit. And it's even broken dynamically by an anomaly that's very similar to the central charge in nAdS3. Now this has had a lot of attention, in particular because there are a lot of interesting near CFT1s that realize this particular symmetry breaking pattern, like SYK, various tensor models, Mellon models generally. So it has appeared now that this new nAdS nCFT holography is an important toy model of quantum gravity that we hope is capturing one little corner of things, but in a really sharp, absolutely minimal way. So that's part of the whole background that people are interested in. I'm interested in a particular aspect, and that aspect is the scales of this theory. Once you have a theory that is not conformal, it is not scale invariant. That kind of goes without saying. So if it's not scale invariant, there's a scale. That means you should ask, what are the physical scales that appear in the theory? These are important questions. Now, the inspiration of the way I developed this subject is that for extremal AdS2 geometries, not just the geometry, but their associated matter, there is a nice way of describing the near horizon geometry, this AdS2 geometry, in terms of what is called an attractor mechanism, which I'll review, that works for extremal black holes. The result I want to push and I want to describe is that for the near extremal AdS2, so one that actually has been deformed, and the matter that is now no longer trivial because it's being now supported by non-trivial matter, is determined by a very closely related attractor mechanism. That's the near attractor mechanism that I'm pushing. It is different, but it is incredibly convenient and has many of the same attractive features that the standard attractor mechanism has. So therefore, it's a nice generalization of the standard mechanism to this context that's slightly different. And it also then, I think, gives a good entry point that one can learn about what is the near AdS, in fact, even all about. So let me jump straight into it and look at an elaborate setting. There are many really elaborate settings for the extremal attractor mechanism, including higher derivative corrections, gauge supergravity like AdS5, non-supersymmetric context that Sandeep has worked a lot on, a variety of different situations that are all very interesting. I'm going to take the basic story, the one that was first developed, as my benchmark, just because I want to start with something that is simple, and it is that thing I want to generalize. So I'll look at 4D theory only, n equal 2 ungauged supergravity, and look at a situation where we have a number of vector multiplets. These are n equal 2 vectors, no hypers, just n equal 2 vectors. So in such a situation, which is a canonical setting for this kind of study, the black hole parameters, is given by the asymptotic conditions on my black hole, is a mass. Their charges for each of our vector multiplets. We have NV vectors in our vector multiplets, but we also have an extra gauge field in our gravity multiplets. So we actually have NV plus 1 different gauge fields. Each of these have electric and magnetic charges. So the key inputs for describing my black hole is a P, Q, and NV plus 1 different sets of those. So those are my charges. And on top, I also have complex scalar fields, because my vector multiplets, they have scalar fields in them. These are complex vector fields. So each of my 1 through NV, not the vector field that's in the gauge gravity multiplet, in the supergravity multiplet, but the one that are in the vector multiplet, they have vector partners. So they're all these complex scalars. They're often being suppressed. We don't talk about them much, perhaps, but they play an essential role in the attractor mechanism. So here we want to actually specify them as genuine parameters of the black hole. They're parameters that we think about as being specified at infinity, and then they are what they are at infinity. They're just boundary conditions. There are no conserved charge associated with them, but there are numbers that actually appear in the solution, and those numbers then is part of the actual, sort of specifying what full solution are you looking at. Now, of course, for extremal black holes, the mass doesn't really count as a parameter, because it's not independent. It's a function of these other parameters of the charges and, in fact, of the scalars. That's how you get the BPS mass and construct that, or the extremal mass more generally. So this is the context, and extremal black holes in this context have been studied really broadly, extensively, in many, many different versions of it from the early days of when people looked at black holes and string theory in the mid-90s. Yeah?
There's no scalar in the gravity.
Yeah.
There's no
Yes.
scalar in the gravity.
There's no, that's right. So vector multiplets have a scalar, gravity does not, so there's one scalar too little compared to the vectors.
The SU2 gauge field is also absent.
Pseudo
The SU2 R symmetry gauge field is not.
pseudo R symmetry gauge field.
SU2, not pseudo.
SU2.
The SU2, well, we have an n equal to, we just have U1 R symmetry. In the n equal to, right? So, I mean, it's interesting to go to n equal 4, but in my n equal 2 theory, I just have a U1 R symmetry. Yeah.
And Abhijit's intuition from superconformal theory is there.
Yeah, yeah, that's right, but in gravity. So how does the attractor mechanism work in the standard case? If I just go and look for what was it that people did, well, the important part is that there's a radial flow. These scalars, as I mentioned, they're being put equal to whatever value you want at infinity. That's how you specify your solution. But then, since they couple to the various vector fields, that value will not stay. They will actually flow in the radial direction and become something else as we move further in. That something else will depend on what charges the black hole has. And as you enter the horizon, something magic happens. That's the attractor mechanism. What happens is that the scalars, they now take on a value at the horizon that is independent on where they started. It depends on the charges that the black hole has, but it does not depend on the initial value of those scalars. That's the attractor point. The attractor point is that you end up somewhere that did not depend on where you started. You got the attractor. So this horizon theory is universal. It's independent of the moduli because these scalar fields at infinity, I said we could take them to be anything, but it matters what we take them. These are basically the coupling constants of our theory, including the actual coupling constant. And the fact that our end result near the horizon is independent of that coupling constant is very important because that means that we now have a sense that our extremal black holes is independent of things like coupling constants. So we have many cards to play in order to study these black holes. And importantly, the attractor mechanism, it determines simply the attractor values for the scalars. And there are nice, beautiful mathematics that says, what are the attractor values of these scalars? If I didn't know them already, say by actually solving my black hole equations of motion, I can find what these things are anyway by much simpler methods than solving actual Einstein gravity equations, Einstein equations. So there's no reason to analyze the entire black hole solution to find these attractor values. They're simply given as function of charges by simple mechanisms such as the entropy extremization formalism or other things.
Are they unique?
Unique? I'm pretending they're unique. They're obviously wall-crossing phenomena and such, but those are, I would say, they're unique because I'm spherically symmetric. So I could have, this is one of the places where I could have made it elaborate. I'm making it not elaborate by basically going to a sector where I don't allow those interesting things to happen. But there are many, many interesting things I could allow to happen, and I won't.
In general, you have domains of attraction. Right?
There are domains of attraction, that's right. And they have to do with things also like, oh, but these scalars weren't, these charges weren't actually quantized, for example. Oh, right, yeah, now that you do mention it. And, you know, but hey, from the point of view of classical, you know, the basic attractor story, no. But there are elaborations that are all very interesting.
Some recent work over the past couple of years, you might well have followed it much better than me, for non-supersymmetric attractors, which claims you can have multiple solutions and basins and so on. I haven't studied all that.
I haven't studied that either, actually. You should tell me about it, actually. I didn't know about this because I've been, really?
We can
Really?
look at it. As I said,
Okay.
might be misquoting something, but there is work like that by Prashant Tripathi and so on.
But what I'm interested in is then not that. It's taken the simplest basic mechanism, but then generalize it in one direction, which is to say, well, but I wasn't interested in ADS. I wasn't interested in extremal. I was interested in near extremal. And the important thing that I should stress at this point is that near extremal appears in two different ways, the word near. There are really two different aspects here. One is that the black holes are, well, not extremal. They are nearly extremal. So the scalars, when you get in at the horizon, well, the horizon is actually not an extremal horizon. It's a near extremal horizon. So they're, of course, not to go to their extremal attractor value. They're going to go to something else because we've added that extra stuff. But on top of that, we're not actually considering just the horizon that basically becomes isolated and infinitely deep in the case of an extremal black hole. We're considering a horizon region. So we're considering the near black hole region rather than the black hole horizon. So there's an entire region. That's another way in which near appears, which is saying that the scalars aren't actually even constant there. So not only should you say, well, what value do they end up with? No, they don't end up with a value. They end up with a function as we go near the horizon. The cartoon, what you should have in mind, which is what I'm going to make more precise, is that the near attractor flow is that it kind of goes in towards an extremal value. However, that extremal value doesn't quite reach. We should think about the entire region as having some kind of exponentially flow in towards the value it would like to go to if this truly was an extremal black hole, which it is not. But since it has this flow in, that is sort of an exponential flow in towards the final value, then that involves, of course, a scale. And that scale L is the scale that we're interested in. It's the one that breaks the conformal invariance, the fact that we're interested in the region that is the approach to the attractor value as opposed to the actual attractor value. So the near attractor mechanism will end up characterizing the approach to what we normally would call the attractor as opposed to the attractor itself, but as a natural generalization of the standard questions, and it's one that we do a good job on. So we want to characterize these scales that characterize this near AdS2 region. And what will they depend on? Well, they depend on the charges. But unlike in the extremal attractor case, they will also depend on the moduli. Basically, our true attractor mechanism, the one that said we forgot entirely about where we started, well, now we mostly forgot about where we started, which means, in other words, we didn't forget. And therefore, it does depend and on what these things are, and we should characterize exactly how they do, how they depend on this. So,
sorry, a question you would probably come to, but if we think of this in analogy with the renormalization group flow, then you might think that there are only a few operators, order by order.
That's right.
Something similar.
That's right. That's right. And that's right. So you could say that each of these operators, though, I want to basically know what coefficients they're turned on by. The irrelevant operators, if I truly went in there, they'd be gone. If I went to my true UV IR, but I don't. I went to my near IR, so they're not gone. So you should tell me, okay, they're on with what coefficients.
And if you want to work order by order, you still have a finite problem because you first take the dimension 6 operators, then the dimension 8. And so on.
Yeah, that's right. That's right. Yeah, that's right. Mm-hmm. That's right. But what we'll see is that we do not have to, we really can package this in a really efficient way that's very reminiscent of what we would have done in the attractor mechanism. In particular, we don't really need to go and find all our actual solutions, which could be very hard because these are now non-extremal solutions. We don't have true BPS technology. There's no sort of near BPS technology a priori that can help us solving equations that means like we are, well, having almost supersymmetric solution. Well, that means they're not, and therefore we can't solve this. We can't use our full technology here.
Sorry, one more question. Even in the case of supersymmetric solutions, you might be interested in the solution where it starts deviating from AdS.
And I will shortly make that argument. Yes.
And that might be more tractable problem.
You are already 4 slides ahead. So what are the scales, just from a physical point of view? Well, let me point out what kind of scales we have, at least some of the important scales. The extremal black hole entropy is a ground state entropy. Since we're in a situation here where our S2, our sphere, is just sort of 4 pi L squared if it has size L, so I can easily compute the entropy. And the one important point I want to make is that when I compute my 4D entropy, then the area divided by my G4, it's really my 2D Newton constant. So therefore, the entropy is a dimensionless number. It's basically my 2D Newton constant. Now think about that as a very large number, but the important thing I want to point out is that it's a dimensionless number. That's what the entropy does. So that does not in and by itself have a scale. It has a large number, but not a scale. But what happens when you go a little bit away from extremality? Well, you add temperature. That means that your entropy is not actually the extremal entropy. It has some extra version away, which is the thermal correction. That thermal correction here is linear in temperature to the first order. We can think about it as being effectively the specific heat, and that introduces a new scale, and it's that new scale here that are called L that is interesting. It's the thing that basically makes L times T a dimensionless correction to my entropy. In the literature, there have been suggestions that actually there's an obvious guess for what that L should be, because I do have a scale here, L2, the size of my sphere. I looked like perhaps I used it to conform my entropy, but I didn't. My entropy was formed just from my 2D Newton coupling constant. It was dimensionless. So perhaps the natural guess for what that L here should be would be that it would be L2, our size of the sphere, in units of our 2D gravitational coupling constant. And that guess seems to be quoted widely, and the answer is that it's totally wrong. We'll compute what these scales are, and it's much more elaborate than this. It's nicer in a way, but it's not that. It's more, it has more structure than this thing. It had to do with people's intuition about this being a gravitational back reaction problem, that if you didn't have back reaction, you wouldn't have the scale in the first place. And but as I say, that intuition I really think, I mean, notable people have written it, Polchinski, Almhairi, and whatever, and Juan even wrote somewhere saying that this was a natural guess, and that's why everybody seemed to think that when Juan says it's natural, that must mean it's right. But no, he should have it not. Do an example. You will find soon that if you do an example that has 2 scales rather than 1, then
Okay, so I just want to understand, but scales. One is the ADS2 radius, and the other, if you like, is the entropy in units of Planck's constant or a scale
Right.
related to that.
And one could imagine that they were similar, but they're not.
Yeah, no, they're not always the same. That's right.
I mean, they are if you don't have, if you have very little structure here. If you were to look at just an near extremely Weiss Nordstrom black hole, yep. But that was because you didn't allow possibilities enough. So let me tell you something about non-extremal black holes. I didn't say near, I said non-extremal black holes. Now, they do have a simplifying feature, even if I'm in this context of n equal 2 supergravity, a lot of scalar fields, a lot of field strength, but actually, I do have something where my energy momentum tensor itself actually has a sort of generalized tracelessness type of condition, because I have my gauge fields really do sit all in something that is traceless. So this helps me to show that my radially symmetric ansatz actually has only a single unknown function in it. I think about it as this capital R here. So to think the thing that sits in front of my sphere. So my sphere, of course, is something at the horizon, and then it gets bigger and bigger and bigger. But if I do know that function R squared, which will depend, of course, on my charges and my scalar fields and whatever, but if I know that, I can also tell you what to get in here. There's only one integration constant, which is R0, which is the position of the horizon. Of course, there's an inner horizon also at R equal minus R0, but I will not pay attention to that. And if I have this just general solution here, I can actually just write down what is the entropy, for example. Well, I have to compute the area, and if I know my R function, if I happen to know it, I can, of course, compute the area, compute the entropy. I can also do some Euclideanization and continuation over here and figuring out what is my temperature. And my temperature, you will notice importantly, is proportional to this R0 parameter, where is my horizon. And this means that what I can think about the extreme limit as is that I take this R0 here to 0. That's how I get to 0 temperature. But importantly, I should make sure that my charges and my moduli are fixed as I take that limit of R0 going to 0. This is how I take my extreme limit. I characterize from the beginning my black hole with having a certain charge, certain moduli that certainly are fixed. These are integration constants. And then as I lower my temperature, I keep those things fixed. I could perhaps think about that as taking my mass down to 0, but that's not very practical. The practical thing would be to take the R0 here to 0 with the charges and moduli fixed. So that's a more practical thing. It's less obviously physical, but it's the way that one can actually do this. So what do we do? Well, this radial function here, I've written it as capital R of R. It's the size of the sphere, but I'm lying a bit. Of course, it depends also on all the parameters of the black hole, like the mass and the charges and the moduli and whatever. So those I consider parameters. I don't consider it a function of those things, but parameters are, well, you know, the other things that it's a function of. So it's really just me lying a little bit. And importantly, it's a function of the mass. And therefore, it's not when we are near extremal. It really has this extra mass that I should take down to 0 at the same time as I'm going down in near the horizon. Now, this is inconvenient, but the entropy is different. The entropy depends on the mass. The entropy is something that doesn't depend on where you compute it. You compute it at the horizon, thank you. And therefore, there's no ambiguity in that. The entropy is a function of the mass. So let me write an equation. This is an absolutely important equation. What happens when I go a little bit above extremality? I add a little bit of extra entropy. The entropy I think about as a function of the mass. So I add a little bit extra mass. How much did I add? This is how much I add. This is my thermodynamic relation. My dsdm by the first law is actually 1 over the temperature. So therefore, what I can see is that my entropy, since what I do here is that I add a little bit of extra entropy that's of order T, because the temperature, the entropy I'm adding is linear in the temperature. And since there's a 1 over T up here, then importantly I find that the way I should change my mass is that I should actually change it by order T squared. So my mass, I should add extra energy, extra mass in it to be sure, but I should add it of order T squared, of order R0 squared. Now this is important because let me try to say, well, there's another way I could compute what the entropy, how it has changed. The entropy I compute, of course, from my R squared function. My R squared function depends on R, the little r, where is the horizon, and it also depends on what mass is that I actually am using, that I have inside my R squared function. So my squared function, it depends on the mass change, because I've added a little bit extra mass, and where do you evaluate my R squared function? Because, after all, the horizon has moved when I add and go a little bit above extremality. Now this delta R here, I already said, was of course, it changes by of order R0. R0 is like the temperature. So therefore, this guy here is like linear in temperature. This guy here, on the other hand, is quadratic in temperature. Therefore, when I want something that is linear in temperature as an added entropy, this thing is unimportant. This thing here is all that matters. This one here is subleading. So at linear order, when I go above extremality, all I need to do is that I can use my R² function, the one that says, what is my geometry? I can use the R² function as determined in the extremal geometry. All I need to do is to go a little bit further out. That was just what Shiraz was suggesting, that that would be a simpler problem. That's a major simplification. What I'm saying here is not just that, oh, you should do this because it is simpler. No, I'm saying that you should do it because it's the right answer to this problem that looked like a more complicated problem. But this is the problem you should study. You should not actually go away from extremality. You should go in the extremal geometry, you should go away from the horizon, and that would be equivalent to going away from extremality. And that will help you determine things like what in fact are the derivatives of the entropy and whatever. You can determine them in the extremal geometry. You just have to understand not just the extremal geometry at the horizon, the extremal geometry a little bit away from the horizon. But,
You're
okay.
restricted to working at order T, basically.
Yes, that's right.
At next order, you would have to also change the geometry.
Yes. Right.
So, Sandeep, what you do also, the near extremality is just broke by the horizon being fluctuating, right?
Yeah.
So the geometry is still.
Yeah, so, I mean, for example, I don't want to anticipate perhaps what you will come to, but you can compute the near extremal response by some degrees of freedom living on the boundary, but that dynamics depends on how the fields approach their attractor value, the coefficient of the Schwarzschild, and that you can determine in the extremal limit itself.
Yes. That's what I'm saying, yes. That's what I'm saying.
So, yeah, so.
I've not heard other people say that, but maybe it's well known. I don't know, but
I mean, that
I've
was
only heard
we
people that they're
also
surprised.
studied it quite a lot, so it comes out there also, but it
So-
ties in with-
So the upshot is that, for example, if I want a heat capacity, then what I need is I need the radial function, this R function here, it's written as R to the 4th. I need it just for the extremal black hole, and what I need to do is to compute this R function, not at the horizon, just by itself, which is what in fact would give my entropy. I should compute the derivative of this function with respect to the radial coordinate, and therefore you get something else, and that something else is the symmetry breaking scale. It depends on moving away from the horizon, but not on the solution being non-extreme. And besides, when I'm saying depends on moving away from horizon, the dependence on moving away is the simplest absolute possible. I mean, take the derivative. I mean, how much simpler could it be than saying I need to go away a little bit by epsilon? You know, this is how we learn to go a little bit away when we learn calculus the first time, right? Take the derivative. This is how you go a little bit away. Linearizing, just the R² function. Okay, so that's what we want to do.
So, sorry, what is the scale that comes down to this?
Well, so this is what we still haven't computed, but now we have a formula for the thing we want to compute, right? That this L here now is this R function. It's derivative of the R function. We haven't yet studied the derivative of the R function, but now we know that is the thing we should try to determine. In the BPS case, in the extremal case, we should try to determine what is that derivative. So what's the approach? But what does it give? Well, don't know yet. So to start answering that question, let's go back again and look at the extremal attractor.
So now you're replacing two numbers, sorry, one number, which was the value, by two numbers. The value of the scale at the horizon now being replaced by the value of the scalar. This is the value of R squared, sorry.
It's the value of derivative. So it's sort of like instead of doing the entropy, don't compute the entropy, compute the derivative of the entropy.
Right.
Yeah, okay.
So I was thinking of the attractor values of the scalars.
Yes.
Um,
Those I have not.
Not yet.
Those will be sitting in the background. I will tell you what they are later, because once we pursue this guy, they will seem like obvious. You will guess. You will correctly guess what they're going to be if you figure out.
You will need to worry about their variations independently
course.
as well.
Of course.
Not just through R squared.
They,
Not just R squared presumably is a
Yes.
function of the variation of order
Yes.
But you might also be interested in the independent variations.
Absolutely. Absolutely. Yes.
I mean, each of them gives a scale in a sense,
Yeah,
right?
that's right.
The
So let's consider the horizon
And
attractor.
you'll only get with the first derivative. So instead of NV numbers, you'll have two NV numbers. Your value and
Yes. Yeah, that's right. That's right. Actually, 4 NV. They're NV complex numbers. So anyway, so for fixed charges, which is what we keep fixed, we have our F mu nu terms in the Lagrangian. So we have these F mu nu squared, so Einstein-Maxwell type terms in my Lagrangian. And since I keep my charges fixed, I can think about these generalized Maxwell terms that are actually being just potentials for the scalars. Because these F mu nu squared have stuff in front of them that depends on the scalars. And therefore, once I take my charges to be fixed, I can think about that as simply being a potential. And this effective potential is what I've written down here. Is something obviously is quadratic in my P comma Q, because my F squared terms are quadratic in the charges. But then it depends in some complicated way by the dependence on the scalar fields through these mu and nu functions, which are the ones that incorporate the special geometry of n equal 2 supergravity. At any rate, the scalars, they're actually ultimately going to be constant in the case of the actual extremal black hole. So what are you going to do? You're going to take this V here and you can say, oh, for a given P comma Q, this is clearly a function of what my scalar fields are. Let me go and extremize over those scalar fields, and that's how I figure out what the value of the scalar fields are at the horizon. So that's great. And after I figure out what their values are, I compute this V here. What is its actual value at the horizon? That'll actually give me what my R squared function is, what my entropy is. And in this case, I actually portray it as my R to the 4 function, because I like that extra power, but it's obviously equivalent. So if I find what the potential is at its extremum, as I extremize over moduli space, I figure out what V is. It will no longer depend on the scalars because I've extremized over all the scalars, so it depends only on the charges. So this will give me a nifty formula for what is the entropy in terms of charges alone and not in terms of the scalars. So that is good. My notation for this in the extremal case is that this R4 function to the 4th power I call I4, because that's the standard notation for this kind of thing. This I4 is, by dimension analysis, a quartic in the charges. The charges, they have dimension of scale, and R to the 4 has dimension scale to the length 4th. So therefore, this will be a quartic function, at least as dimension analysis goes. And the reason we really like to write R to the 4 rather than R squared is that in simple cases, such as n equal 4 supergravity, this I4 function really is something that is literally a polynomial in the charges. So like P squared Q squared minus P dot Q, whole thing squared for n equal 4. There are other functions where it's a polynomial, perhaps a more complicated polynomial. In some other cases, more complicated than general n equal 2 theories. It not actually is a polynomial, but it certainly is something that still is order 4th in the charges just by scaling. So it's some kind of function at I4, and I'm going to consider that you guys have found that I to the 4 already because you've studied the extremal attractor mechanism a lot. Whether or not you actually did it, I'm going to consider this I4 a known function after study of the extremal attractor mechanism. In simple cases, it certainly was known. In complicated cases, it's been characterized in various ways. I'm going to consider I4 a known function because if I just knew that, it turns out that I know everything I know. In fact, everything I need. In fact, if I knew that I4 function, so some function of the charges, I could actually go back and tell you what the scalar fields are. So I instructed you that you should take the potential and you should extremize over the scalar fields. And that could be kind of complicated because it gives you a lot of nonlinear equations. But as it happens, I know the solutions to those equations quite generally. You should take my I4 function here, which is some quartic function of the charges, and then you differentiate with respect to the charges in some symplectic invariant way. And then in this kind of way here, you actually find some nice expression for some scalar fields, xi comma fi. This is symplectic notation for the scalar fields. The simplified way of looking at it is that it's a projective parameterization of the physical scalar fields. You should just take these xi's here and take ratios between them. And then that will give you your zi's will be the ratio of these xi's comma x zeros. Your f's, on the other hand, incorporate your prepotential. So at any rate, this is some nice nifty formula for saying that if I know I4, I know what all the scalar fields are as well, and I can give you even an explicit formula for what they are. So really, go find my I4, please, for your favorite prepotential, and that will be some algebra, but once you've found it, it actually encodes everything that I would possibly want to know.
Exercise complex, please.
my x's are definitely complex. Yes.
That's why
Yes. Yeah. But there's one more x now.
that's
Right.
simple.
So,
And that's the critical issue.
so now we want to move away from the horizon. So the radial function at the horizon depends only on the charges. But obviously, as we move away, it'll depend a little bit on where are we going. We are going out towards the scalar fields at infinity. And therefore, we have many different options. We're no longer literally at the attractor. How can I characterize those options? Well, let me give you an algorithm for how to characterize them. I'm going to imagine that I already studied, like I told you to before, studied my mechanism that says, given my charges, what are my scalar fields going to be? So that I'm going to consider a known function. If I know the charges, I know what would be attractor values of scalars. But now we have the opposite problem. I'm saying, what if I actually impose some kind of values of scalars at infinity? I'm going to say, well, what charges would have given exactly those values as their attractor values? So this is the same function as I wrote before, where before I said, look, I consider the charges as some inputs that tells me what are the horizon values of my x's. Now I say, well, actually, these are inputs now. These are my horizon these are my values at infinity, and I'm going to map back towards some would-be charges that would have given these guys, but at the horizon, you know. But this is not actually how I read this. I say that this was a known map, and once I know the map, I imagine that at least locally I know the inverse map as well. Therefore, if you tell me what scalars I want at infinity, you can figure out what charges would have given those scalars. Those charges are the ones that are called P infinity, Q infinity. They aren't actually charges at all. They're not even dimension of charges. They're like scalars. So they're the one parametrizing the scalars, but it's a nice parametrization. Why? Because in the extremal case, the full attractor flow has a beautiful radial function. The radial function now is given by this I4 function that I already had introduced. And now how do I get my full radial flow? I get it by taking my charges and shifting them in this particular way by my P infinity and Q infinity. So the reason that these Q infinities and P infinities are nicely introduced in this particular way is that they're great parameterization of my scalars, is that they tell me how I should move away from the horizon.
And this makes sense because it's projective.
Because it's projective, exactly. So this is why I needed as many of these as and in fact, there's an integration constant as well, or whatever. But this is why I need a little bit of redundancy to have as many charges as I had scalars.
So at infinity, it's all that guy.
Yeah.
At zero, it's all this guy.
That's right.
This I didn't know. This is a general feature, or is it true in this case of n equals to special geometry?
N equal to special geometry.
And is it even more general? Very beautiful.
I have speculated that it was more general, but since writing the paper, I started checking, and I am no longer speculating it quite so strongly. but I mean, hey, I only said it was true in that case. I was just guessing that it was useful in general, and now I'm beating on a student to determine. But you just need this example. Why can't you work it out? Well, because it isn't true, sir. Oh, right, okay, fair enough.
Remind me, what was your definition of the variable r, please, in the metric?
The little r?
Little r.
So that was the r squared. I had my little r squared minus r0 squared, and that was how I parametrized my. So I actually parametrized it in such a way that the function in front of my dr squared, my grr and my gtt were inverses of each other. So therefore, that's right. So I parametrized it that way, and
So it's a nice parameterization, but is there geometrical significance to this r?
no. It's the one that it simplifies greatly certain things, but
But you have some sign or something.
No, but the radius of your two sphere depends only on r, right?
at infinity.
All along the flow, right?
My capital R, right? But he's talking about what is the significance of my little r. The little r was sort of, well, it was the thing that parameterizes the capital R.
So it would have been even nicer if this was true with a clear geometrical meaning for us.
Yes. No, it's, yeah. And but it is true, and it's you know,
Yeah.
it really Denef and Moore and whatever, they basically have this. They just don't write it. They have other fish to fry, so they don't formulate it this way. But what?
They don't write it in a way you can understand.
So now what I needed to do was to do my radial derivative of my R4. How does that actually work? Well, the radial derivative is now becoming a derivative in charge space. Because remember that I had my shift in my R dependence here was basically shifting the charges. So therefore, to take the radial derivative, what I need to do, I can actually trade taking the derivative with respect to R as taking the derivative instead with respect to P and Q. So therefore, I can take a derivative in charge space of my I4 function. So my I4 function was a function of just P's and Q's, and now I say, you should take a derivative of that. How hard could that be? It's a function that for simplest cases even literally a polynomial, but in other cases it's a function that's of homogeneity 4. Go take derivatives with respect to Q and P, so that gives you a gradient, but then you're going to say, okay, nice, I computed this entire gradient, that's a whole vector, a symplectic vector. What direction should I take in order to get my specific heat? Oh, take the direction where you dot with your PQ characterization of your scalar fields. You know.
Sorry to interrupt, but just to make sure I understand. So capital R at the little location little r, is capital R of the extremal black hole, but with these renormalized charges.
That's right. That's right.
Yes.
Mm-hmm. Right. So this is the near attractor behavior, the nAdS2 behavior. It actually follows from the attractor geometry, but I need extra data. I need to know what are my boundary conditions at infinity, and I need to package it differently, as in differentiating with respect to the charges instead of literally computing it. But that's about as simple as it could be.
The approach is just a direct straight line.
Yeah. So,
This follows, of course, from your last equation, but just to make sure, this is related up to some constants, just in terms of the derivative of R to the 4, capital R to
Yeah.
the 4, with little r, right?
right. That's right.
And because capital R is the same function, but just as a function of the renormalized charges. It's
Yeah.
just
So here,
differentiating along that.
so one corollary that comes from this is that this was a quartic function. What happens when you differentiate? You get a cubic function. You know, I mean, this was not deep, but it was important, actually, that you get a cubic function of the charges in all cases. And in a way, what you did was that you removed one charge and you put in the modulus instead.
So was it a homogeneous function? The quartic function?
The I4 is a homogeneous. It's a homogeneous of 4, and I'm saying that in some of my favorite examples, it's even a polynomial of 4th order, but no guarantees for that one. That's just because the simplest examples are, well, simple. So, you know.
Again, probably you will come to this, but just if you try to construct the 2D description, then you will be able to map to an effective JT type of model, and the coefficient of the R minus lambda term, the dilaton effectively, will be the radius of the 2 sphere, and so it's how it's deviating away, which is setting the scale of the Schwarzschild. You see,
So first
that's
derivative is the
is the scale of the. It is the analog of the scale J in the S phi.
So it's this derivative of the that also connects it to the specific heat directly.
Yeah.
I see.
So that's how it works.
I see.
That's right. So, now this breaking scale, the breaking scale, as I say, is effectively the radial derivative of R squared. But now, as was reminded us several times, there were these other scalar fields, Zi's, that get to their horizon value Zi, and that's the horizon value at the extremal case. Now, how do you find what they are in this case of how they move away? Well, you will be unsurprised to learn that you have to do exactly the same thing. You have to take the derivative in charge space, and the way you sort of take the radial derivative of this guy is that you trade it for a derivative in charge space. So therefore, if you've already worked hard again to find what were all my horizon values as function of charges, you may literally know what these functions are as functions of charges, and it should not be hard to go and take their derivatives to find as a corollary, basically, what is their approach towards that final value. The approach toward that final value is take the derivative with respect to the charges. So I'm imagining you study the horizon, the extremal attractor mechanism really carefully. You have already big sheets and books of these little things in your notebooks. What is it as function of charges in your favorite examples? Go take derivative with respect to the charges, and you will now find the approach towards that final stuff. is really a corollary of what you already did. This is why I'm saying that the nAdS2 is just a little extra thing on top of the attractor.
But Phil, first of all, small question, which is you don't have the index capital I on the Z's. Did you mean this for the projective coordinates? Or
No, so here I actually am writing for your convenience for the real guys.
Okay.
Because here I'm saying take any one of them, but now this one here is itself a symplectically invariant operator. That symplectic invariant operator I can identify with the radial derivative, which is, you know, geometrical and therefore not depending on symplectic frame.
And
So.
Is this because just as for capital R to the 4, when you wrote the full radial dependence, you simply took pi and replaced it by pi plus p infinity r?
Right. So once this happens in the I4, but remember that my scalars, they actually were functions of this I4 as well. So therefore, I can basically, to take the radial derivative of these guys, I can sort of take them through and just.
Good. So, it's
So
actually,
therefore,
that ansatz is true for all the
So the whole geometry, not just R, becomes slice by slice what it would have been at the horizons, but with renormalized.
Exactly. Exactly. So.
This, sorry to ask you. So this, but in a sense, there are different scales in the end, right? It's capital.
Yes, right. That was, as I say, I revealed early on, for whoever thought there was only one scale, come on, right? You differentiate this thing, it depends on the object upon which you do the differentiation, you know.
So in particular, if you take very asymmetric values of charges.
That's right. That's right. So let's do an example of that, the STU model. So just pre-potential x1, x2, x3, or S times T times U if you prefer, and we simplify charges in the way where they're either electric or magnetic, so it's all very simplified. This gives me an effective potential, because I do these things very simply. That just looks like this. It depends on my Q0 and my P1, P2, P3, which in fact I can think about in certain setups as they being ultimately a 6 torus, where the Y1, Y2, Y3 are the sizes of each of these 2 tori, just the sizes here. They're not complexified because I've chosen simplified charges in such a way that everything is real. So this is a potential that has a nice interpretation, and if you're familiar with the interpretation, that's very helpful. If you're not familiar with it, I won't discuss it. I will just say it's there. But what do? You go and take your standard algebra book and extremize your potential and say, okay, good, that should give me what are my moduli y here. What are they at the horizon? Well, they are some function of charges. My yi is effectively proportional to my pi with some universal factor in front. So that is my value. It's well known. And specifically, it's independent of the asymptotic value. And when I take that and put it back into my potential and I compute the corresponding entropy, I find the formula, the square root of q of a quartic that is very well known for this particular case. So now what is my attractor mechanism? That's saying, well, but that was the extremal attractor mechanism. Now we have something else. We have some other moduli at infinity that are our inputs. Okay, we should paraphrase those in terms of some would-be charges that would have given those y infinities. And then once I have that, how do I find my symmetry breaking scale? Well, I should obviously invert this equation here and find my p infinities, q infinities in terms of my y's. Very good. But after that, I take this and take my derivative. Remember, this was literally just the product of 4 different charges. So each time you take a derivative, you remove one of the 4. So therefore I get 4 terms, depending on which one of the 4 it was that I removed. So I get 4 different terms. For each of these, I need to find my inverted p infinities or q infinities, which of course was not all that hard in this case, so I could invert it. So here is my final expression for the length scale. A length scale that depends, obviously, on the moduli at infinity. There was actually also a dependence in there somewhere of G4, but I've traded that as a product of my 6 torus and an R11, if this was an M theory. So the reason I have an R11 here is that it basically came from the 4-dimensional Newton coupling constant by me taking some 6-dimensional volume out. So this way I get a nice expression where the full scale is something that is quartic in the charges, but sort of divided by one or the other of the 4 charges, so that it's cubic in the charges. But they're different terms. And this, I'd say, yeah, so this is a non-trivial dependence on these various things, as Shiraz says, oh, now you could, for example, say, well, if these were all very similar, for example, if they're all identical, well, then that you would in fact get the Weiss-Nordstrom black hole, and there would be only one scale, and it would be the scale, and therefore the only thing you would get, in fact, you would get a funny factor of 4 that would differ, would the only thing you could get. And if you do everything with twiddles, as some people do, then they'd say, well, there's only one scale. However, this really is a function, it's a non-trivial function, and of course, if this was a much more complicated example, it would be a much less trivial function. And in fact, it's not just any old function, because what if I were to make a hierarchy between these various charges? If I make a hierarchy between these charges and saying, well, you know what, I want my Q here to be very small compared to these guys. So therefore, this division by here dominates over these guys. Then only this guy matters. Then what you get is that once you have a hierarchy between your charges, 3 and 1, then this scale simplifies greatly, and this actually was called the long string scale for fibranes that are wrapping some divisor inside my Calabi-Yau, and therefore it has triple intersections, and these triple intersection number in this particular case is just P1, P2, P3. So what you should read like this is that the natural scale was perhaps 2 pi R11 for you, but you actually get this extra lengthening factor by this large triple intersection number, and that's of course pretty famous and has interpretation that's microscopic and all that. So, you know, this is what you get. This is why actually originally I took my L scale introduced in terms of the specific heat, but with funny pi's and 2's in front that weren't perhaps entirely obvious. They were done in such a way that this came out on the nose and gave me, you know, just what we normally call the long string scale, because I didn't want to introduce things that were, again, off by something, because I had no particular reason how to normalize my length scale from the macroscopic point of view. It was just something that was that order, but I decided to introduce something that gave a more natural value here. And then the LIs, the ones that corresponds to, what about my dependence of my y coordinate? How do they go in? Well, they look pretty much exactly the same as these guys here, except that you sprinkle pluses and minuses in here. So therefore, what you really can say is that I have 4 scales. It corresponds to these 4 guys independently. These 4 guys really are independent scales. And could they all be of the same order? Yes, if everything is of order 1. Or could they all be different? Yes, they could be parametrically different if something you tune to be big. But if you tune nothing to be big, well, then yes, they're of the same order. You know, that's how it is.
And sorry, if I can just make a comment along the lines we were discussing earlier. So if you look at then the near extremal dynamics, you can characterize it in terms of a Schwarzian mode of the near nAdS2 boundary, but you also get phase modes for all the gauge fields.
Yes.
And all of them break the conformal invariance.
Yes. But did you do this?
Yes, yes.
I did not know.
Okay.
I did not know, because that's, anyway, so we've worked out some of this, but not published it, so it's possible that I clearly need to look at.
So now we can talk about it.
What? What is?
We've not yet had the chance to receive the reference complaints.
Yeah, yeah. But
No, but just to say, I mean, it ties in
no.
beautifully.
Now, I do not quite know what, that's right. So that's indeed the question now that I've used 50 minutes or so. So whether indeed I should explain to Sandeep half of what he already knows, or whether,
No, I can talk to you
because
later.
what the remainder was in fact, how does this fit into Schwarzschild? And so it's a little bit separate, and this is sort of work in progress. We have not fully worked this out, so maybe it already has been worked out, although I have been trying to pay attention to literature, but there are so many people that are writing things about this. So at any rate, this is certainly something we would like to do, and I do have a perspective on it then that probably would be different from the one that Sandeep is doing. So it's, where do these scales come? Are they really in the microscopic theory? And of course they're in the microscopic theory. And do they sit in the Schwarzian-like theory? Yes, of course they do. We have a generalized Schwarzian theory where each of these different scales, they turn up. And it's interesting to see how exactly do they turn up. So now for that, we should go and study matter fields and their fluctuations.
Sorry,
Yeah.
you must remember, I might not stay till the end, and I'm dying to ask you a question, which let me ask now, which is that very beautiful ansatz you had for the full renormalization
Yes.
group flow, which we talked about. oftentimes the way the non-SUSY attractors work is a relatively simple variant where you flip some charges,
Yeah.
etc.
Well,
And
that's no.
There's that
No.
ansatz.
Only for it's very special. And you're saying these flips. I know that is often being said. I do disagree
It
with
doesn't
it.
always, and I don't want to take away from the
It definitely
people
does not always work.
Yeah.
I mean, look,
But
it really. So there are simple cases where you can persuade yourself that yeah, of course it works. But then if you go and look for these slightly less simple cases, actually it doesn't. In fact, in particular, and the reason this in part is a problem is that the dimension of moduli space is different. There's a factor of, there's 2. So anyway, so this whole thing about even the number of scalars versus the number of charges, that's a problem. You lose one scalar. So your formula is totally different, actually. So it's, the numbers don't even fit. So
in particular, that ansatz for the flow also.
that does not fit. You can go to very special cases and it will fit you, but if you want the full general thing, which is what I wanted, I've written everything in symplectic form, so you could take extra charge, arbitrary charges, arbitrary everything. No, you need very specialized choices in order to make it work, which of course you could. At any rate, so we've studied also fluctuations, and in fact written many papers on fluctuations around these different solutions here, and I should just say that, well, it's kind of non-trivial in n equal 4 in the n equal 4 supergravity. We have very beautiful answers for those too, and one of the answers we have is how this scalar field, it has a conformal weight h equal to 2. 2 being more than 1 means that it's irrelevant, which means that it sort of has an effective mass and is being fixed as you get in towards the the attractor, and we have a good characterization of that.
I didn't understand. You studied fluctuations of what, please?
This is just taking, so the field strength and the scalar fields, they're coupled to each other. So as we are actually, so as we take fluctuations around our attractor geometry, then they couple to each other in sort of kind of some nonlinear kind of way.
And still uncharged scalars.
There's these uncharged scalars, but the field strengths and the charge, they kind of mix to each other in a very non-trivial way. And one thing that is very nice about that particular mixing is that it is such that the scalar field, in the end of the day, gets a really nice conformal weight. That conformal weight is 2. It means that it's gotten sort of a mass, and that, but the mass is sort of really, look, 2 is the nicest number that's bigger than 1. So, you know, just saying. So what I actually wanted to do was to say that, well, but this gives us an interesting thing, and this has to do with what Sandeep is saying, is that we should go and start studying our gauge fields in nAdS2 now. And the gauge fields in nAdS2 is tricky because they don't have any degrees of freedom, really. They are, after all, basically, you know, only pure gauge here. But let me try to make it a little bit more specific. How do I actually analyze gauge fields in nAdS2? The way I analyze the gauge fields is that I write my 2D gauge field and saying, well, I could dualize it into scalars. Basically, it's either something that's a gradient, or it's a cross gradient, so it's either a d of something, or it's a star d of something, or it's a harmonic mode, which is both d and star d. So this A0 here is both closed and co-closed, and we can think about that as literally being the one that's pure gauge, that is written, say, as a pure gauge, but where the pure gauge function even is itself a harmonic function.
I could ask a general
Yeah.
Gravity in 2 dimensions is -1 degrees of freedom.
That's the next slide. Or 2 slides.
I'll just finish if you don't mind. So it's enough to eat up one of the scalars.
Yes.
Gauge theories in 2 dimensions have 0 degrees of freedom, so they don't eat up any scalars.
Mhm.
So it looks like it'd still be left with nv-1 scalars left, propagating degrees of freedom inside.
Oh, right, but there was one extra scale. This r squared scalar is the one that's being eaten up. So the r squared was not, I did not treat that.
Scalar for r squared?
Yeah, that the r squared, from the 2D theory point of view, this sphere size is actually the dilaton. So that's the one that's going to be eaten up. So therefore, you know, my vector fields each have their own personal complex scalar, and the gravity does not. But it's kind of takes the r squared scalar, and that becomes part of the.
That's an independent degree of freedom from this.
Right, from the 2D.
On shell, it's not independent.
Yeah, on shell it's not. That's right, but it's the one that's being eaten.
Right. Okay.
So that's right. So.
I mean, yeah, all these scalars in these multiplet
Right, but what I'm interested in now are actually these non-propagating guys. So this one here was written sort of in Euclidean space, but of course what we normally do is that we'll say that in Lorentzian space what really happens is that one of these guys here I can just gauge away and the other guy actually becomes gone because of a constraint, and this is why even though it looks perhaps like I had 2 degrees of freedom here, I actually have nothing. But the subtlety comes though with what about the harmonic guy? What about the harmonic guy? Was it pure gauge? Could I gauge it away? Or was it something? And that matters there where it makes things are very different between ADS and the disk. The harmonic mode, I'm arguing, is physical. Let me write ADS2 here in conformal gauge. This is what it is. It looks like a disk, but importantly, it has a conformal factor that blows up near the boundary. So therefore, if we say, oh, but everything is conformal here, it's just a 2D gauge field after all, it's conformal, couldn't I remove this away? Well, do be careful. This is a conformal factor that blows up potentially. So therefore, be careful about moving it. Let's actually try to ask our boundary modes, our harmonic modes, what exactly do they look like in these complex coordinates? They look really nice. I can solve the harmonic equation really easily. It's either holomorphic or anti-holomorphic. These are my possible gauge functions. So I can find solutions like this A mu here that actually is obviously pure gauge. But now wait, because this A mu here that I'm writing in this particular way is normalizable A mu in ADS. However, the gauge function that I'm using in order to generate this gauge field is not normalizable. Why is it not normalizable? Because the boundary geometry is blowing up. So therefore, this A mu that is written and looks incredibly pure gauge is in fact not pure gauge. It's pure gauge of a gauge function that is illegal. And therefore it is, in other words, not pure gauge. It's a normalizable, it's a physical mode. And this physical mode is written in a way where locally it has absolutely no energy or anything like that, but it does have 1 degree of freedom, this harmonic mode.
Basically A mu on the boundary. Right?
What?
This is A mu restricted to the boundary?
That's right.
And I'm very confused here. I thought deviations from ADS2 were important in your stories.
Yeah, no, that is fair. So now you're right. So now I'm analyzing, that is fair. I'm analyzing ADS2 quantum gravity now. So now I'm not, so the deformation that actually will take what he does is that we have to, I'm trying to find out what are the important modes. Okay. These important modes would indeed have 0 action because I've just determined now that they're the nothing modes. You know, they have nothing. But then in order to make them to something, I need to do what he was saying, which was to give them an action, and that action is actually by differentiating as I go away.
So this is the 1 by J of S, right?
Yes.
The action will actually be 1.
Exactly. Right. So what happened to gravity? Well, what happened to gravity was what was just pointed out by Shiraz also. We have 3 components, G mu nu. We have 2 diffs. Oh, and we have 2 associated constraints, so therefore we are down to about -1 degree of freedom. So we need to couple to a scalar field in order to have nothing. And the actual nothing theory here, we can think about it as there being sort of this one Liouville theory, but well, let me not take that point of view. Let me instead take the point of view that is similar to that of the Gates theory, where I'm trying to say, let me literally again track it down and write away my fields. Let me try to dualize my G mu nu to 2 scalar fields. This corresponds to me saying that, well, I could write this as some combination of derivatives acting on some scalar, or some other combination of derivatives acting on some other scalar, and this is how I'm going to try to make my G mu nu into 2 scalar fields, which basically are the scalar fields that would be dual to these diffeomorphisms C mu. So I'm saying that my metric is pretty much pure diff. Those pure diffs, could they not themselves be written in terms of scalar fields? Yes, sure they could, couldn't it? So I can try to represent this thing in terms of just scalar fields. But the important point again is going to be this harmonic type mode here, the one that can be written in this form and in that form. Because in Lorentzian signature, what you can do is that these guys here, you truly can remove these G plus and G cross. These are 2 different graviton polarization states you really can remove. However, the boundary state you cannot move, the harmonic mode, the one that can be written in both these different ways, you cannot move. There's an interesting perspective on this that might very well say, no, you're kidding me, right? Well, let's try to think about AdS2 the way we normally would analyze a world sheet. We'll say this is just a two-dimensional surface. I learned about it in Joe's book or somewhere else. So how is it that I try to actually get my entire metric and get rid of it by basically by making it into pure diff? And then after that using a conformal symmetry to get rid of the rest. One of the key questions there you should ask is there any residual diffeomorphism symmetry after you've actually already gauge fixed your diffeomorphism away? There could be. Those are the ones that are called conformal killing vectors. That's your residual conformal symmetry, the residual diffeomorphism symmetry that you have after you've already gauge fixed your diffeomorphism symmetry. There's an interesting thing on AdS2 that is different from a disk. There are no normalizable conformal killing vectors. Again, you would have some candidate conformal killing vectors like these guys here, and if we'd been on a disk, we would have said, oh yeah, the low guys, the 1z and z squared actually would be normalizable on a disk. However, again, because of our blow-up factor, these conformal killing vectors are not normalizable on AdS2. So these are not legit conformal killing vectors. We simply have no extra conformal killing vectors. We have no extra moduli in our AdS2 quantum gravity. But we should also ask, oh, but are we really sure that we get all these G mu nus? Could we really reach them all by diffeomorphisms? Or could there be some of these harmonic modes that I have lost? Those would be the ones that we call quadratic holomorphic differentials. They're the harmonic modes that are introduced, the ones where I said, oh, there were different ways of writing them, but there was a redundancy. In complex coordinates, quadratic holomorphic differentials correspond to something that looks like this, so that it corresponds to your metric looking like coming from a diff, but the metric itself is entirely holomorphic. It's a quadratic holomorphic differential. And again, we ask, are these guys actually normalizable? Well, if we'd been on a disk, no good. We would not have quadratic holomorphic differentials, but if we are in AdS2, we have an infinite set of quadratic holomorphic differentials. These are all very good. These are perfectly good quadratic holomorphic differentials. They are formally, of course, written as purely diffeomorphisms, which is why you should be very suspicious. But again, just like the vector field, these are the kind of diffs that are in fact non-normalizable. They would have been normalizable if we went to the conformal frame given by the disk, but they're not normalizable once we're on AdS2. And therefore, these quadratic holomorphic differentials are good. We have an infinite set of quadratic holomorphic differentials on AdS2. In fact, an interesting way to package the information I'm giving you, yeah.
Which is to say that the diffeomorphisms that formally would take you from one to the other are not allowed.
That's right. That's right. That's right. They would have been allowed if you threw away the overall conformal factor, but well, that's the whole point. You're on AdS2, not a disk. Right? Now, it's really interesting, this thing to me. The disk and the AdS2, of course, are topologically equivalent, but related by this conformal factor that diverges on the boundary. So what happens? In fact, the Riemann-Roch theorem is an interesting perspective. How many conformal killing vectors you're supposed to have, and how many quadratic holomorphic differentials? 3, thank you. And what we learn in our textbook is that is very simple. There are 3 conformal killing vectors and no quadratic holomorphic differentials for a disk. So that's how it works. On the AdS2, there are none of these guys. And there are infinitely many of these. However, you can write this regulated sum down for all the quadratic holomorphic differentials, and you find that there are -3. Find -3, and for those of us who nowadays know all the Schwarzschild language, the reason that they're exactly -3 is that you can do any conformal transformation except the SL2. That's the -3. So therefore, there's a reason that my renormalized sum give -3. I'm saying that really is a good way to think about this, where we have many actual modes, but if we count them, there's a good way of counting them that gives -3. So, you know.
Have you counted also the SL2 0.0?
Yes, that's right. That's right, exactly. So my regulator was such that if I counted also the SL2, I would have gotten 0, but I shouldn't. And therefore, my quadratic holomorphic differentials, they start at 2 and up. They don't include the plus, minus, 1, and 0. They start at 2, and that's why they don't manage to give exactly the 0, the infinity. Just because you see infinity doesn't mean it's 0, right? As we learn in quantum field theory. And
the regulation scheme here is the one that, using which you can prove
yes.
the one that is relevant to the index curve.
That's right. That's right. Yes, that's right. Yeah. So from this point of view, we've identified my modes and have this sort of geometrical way of looking at them, that my gravity sector is actually a set of quadratic holomorphic differentials. My gauge sector is a set of pure gauge one forms, so holomorphic one forms. Now I need to find what is my effective low energy action for these guys, and there I use sort of standard results from the literature, where probably I should read more of the literature to leverage them, but at least the way I package them for now, before I've written it up, is that I use what Juan and Stanford did, is just computing the boundary actions directly and plugging in my modes, and then what I get actually is a Schwarzian type action, which importantly has not just a Schwarzian, but also this extra piece here that depends, that came from the gauge fields, and importantly it depends on my scales, these scales that I thought were very important. And each of these things, they come from basically saying that this thing here was fully topological. If my R and my nus here were constant, then this thing here would go together with my bulk terms and literally give nothing. Therefore, I have to take my derivatives of these guys in order to get anything. And the anything then is the thing down here. So this one here becomes this R here is derivative is L, and the derivative of this thing here is this.
What was tau, please?
Oh, that's a reparametrization mode on, yeah. So it's it's on the boundary. It's a
Cutoff surface?
you can call it a cutoff surface, but I don't like to cut it. I would say that. So the parameterizes at a cutoff surface is the way people often talk about this, but I don't like that. I'd say that it's more like a conformal structure at infinity. So I would say that it's at infinity, thank you.
But now you're taking into account the breaking of SL2R, right?
Yeah, yes.
And you're going to the boundary in this one deformed geometry.
In the one deformed, right. But I'm saying that I'm still out at infinity. In the same way, the normal ADS, I don't like, I mean, you could regulate, of course, but I'd say that it's important in normal ADS that we say what the boundary really has is that it has a conformal structure. It does not have sizes, right? Similarly, this guy has a conformal structure. It does not have size.
And infinity is non-singular in this case?
Yeah.
I see. This breaking of the running of the thing doesn't make it singular? At infinity, you have your scale as infinity. Do we have to regulate it?
I think he's doing it in the same spirit in which you take
You cut off but far away.
in ADS, as in you have to do holomorphic renormalization. You know, you
Yeah.
first take a cutoff, but it's in the asymptotic region of ADS, and then you take the cutoff to go to zero. And what he's saying is that if you do it carefully like that, then there's no dependence on that cutoff length.
There's no dependence on the cutoff
So
left,
it's
right?
in that sort of spirit.
But that's the same thing as cutting it off in this intermediate region, right? I mean,
Well, but for me, right, but there's a difference there, I think, where you should make your estimates right. Because now you could say, oh no, but once I actually cut it off, then you should actually go and say, no, you know what, your conformal killing vectors, they're just fine, thank you. And your quadratic holomorphic differentials, they're pure gauge. Because they're pure gauge of functions that would become bad once I take my cutoff away. So therefore you could take the view now that, no, once I'm cut it off, it's a disk, thank you. But I said, no, but I really don't like that. Because that means that I didn't, the degrees of freedom that actually became physical, I have now overlooked. I've said, oh no, they're not physical at all, they're pure gauge. I said, no, I would like to framework where I have the right guys before I take the limit, and then as I take the limit, I still have the right guys.
Sorry, one more question. Those Li terms are basically such waves mixing between the conformal factor and the phases, right?
Yeah, I think the lambda i's came from your gauge
Yeah,
field.
I think about it just as a derivative of my gauge functions here.
Yeah,
That's the Li's.
So there were the Li's. These were the ones I had, which was basically the radial derivative of my Zi's.
I understand, but I thought that would basically multiply the phase mode,
Yeah.
the phase mode for each of the U1s, and
Yeah.
that mixes with the graviton is what you're seeing.
Yeah, that's right. That mixes with the graviton, that's right.
The lambda i's are from the gauge fields, right?
Yeah, that's the lambda. I called him capital lambda on the previous guy, but that was because I only had one gauge field. Now I have a bunch. So this is the gauge mode. This is the one that is, D of that is the gauge field.
Can you show the slide where the lambda was defined?
What?
Where the lambda was defined?
So that was so previously I didn't actually define it for the whole set, but just, it's that lambda.
Ah, okay.
It's that lambda that then can have a coefficient in front. So it's really that lambda that is, that particular profile becomes an actual quantum mode that's that's dynamical. Right, so
And then you'll also have, just along the lines of what Shiraz was saying, and what Satyav et al. Found, also a term quadratic in the lambdas, lambda I, lambda j.
yeah, so I hear, but yeah, I have not quite persuaded myself. Actually, so yeah,
I
see,
haven't
so
thought
this
in
one
your
here.
language,
So this one here is, yeah, so this one here is,
You found that.
Yeah, I
Yeah, yeah.
found that more. But okay, it'll be interesting to talk.
I think there are slightly different rules one can pursue that of course should give, they don't have to give the same results, they have to give results that are consistent with each other. I mean,
You're saying your cutoff, how you cut off.
yeah. So,
That operator is also equally relevant.
equal one?
Yeah, I mean, they combine, it's actually a perfect square involving the phase mode and a mixing to gravity. When you expand it, you get a coupling,
Cross term, yeah.
cross term, and then you get a term quadratic in the phase mode.
Okay,
Lambda I, lambda j.
I have not seen this. So you had a paper like this? Or is it just,
Well, for the
yeah.
1 gauge field case, it's easy to
Oh,
see,
yeah,
and then
okay.
for the multiple, it
Yeah.
sort of follows just from.
okay, I have not. But you didn't do. But also, certainly didn't. Did you include the functions in front? These news and eyes,
Not
whatever.
in the
The whole.
paper,
Okay,
but
so
sort of the same rules.
yeah.
Where did that come from? It is the same scale term? Or?
Yes, yeah. So I only have this. I only do this term here, and then I hear about this a squared stuff, but I'm still on the fence on that. Especially, I guess I wrote a paper about that a squared term like 10 years ago, and I still haven't gotten all the Rotten Tomatoes washed off. People really didn't like it, but that I put an a squared term on the boundary. But a boundary on nAdS2. So what?
Because of
No,
supersymmetry,
just from the
not present.
dynamics of
No, the fact that it's not present.
That what is-
It should be present here though, so it's just
Yes,
very universal.
what you're saying, but
From the point of view of the, yeah.
okay. But let me also, so now, I think it's time to just summarize, and I think I have said all of this stuff and look forward to a lot more discussions, and I'm happy that they decided to talk about this because it's something that I will learn stuff too. Okay, so thanks for your attention. It looks like ICTS used to have a small audience, and now it has a vanishing audience.
No, slow down. Slow down.
I'll see you.
Okay. ICTS questions?
No, we don't have any questions.
How about here? More questions?
But well, yeah.
I'm going to ask you the question that Sandeep would have asked. That you should ask. Which is that you invent some rules, but in a way, once you go away from the real ADS, the real rules are that you do the whole geometry. And then you try to see, one sort of interesting question is, what about the whole geometry can you figure out? Let's say you want to compute scattering amplitudes or something like that, of the whole thing. Now there's no real cutoff of the whole geometry.
But sir, wasn't it argued that you want to look at linear in temperature, which is a derivative that you want to take?
Yeah, for thermodynamics.
Okay.
But now suppose you want to, for instance, these Schwarzian modes and so on, you want to do some dynamics around it. One set of rules that are very clear is that you just work with the whole thing up to flat space and sort of try to integrate out this region, this
Yes.
geometry, and
Yeah.
then explain what role the Schwarzian and the space modes play in that picture. Should be some effective theory of this neo-horizons region coupled to the outside,
Right.
and that should give you an unambiguous set of rules for this cutting off.
Very good.
And one
So for that, I do have one computation along those lines that I think is that it's an old computation, but again can be revived now, which is this Das-Mathur absorption cross-section computation. So what they did was that they were studying D1, D5, and had really a particular UV theory in mind and whatever, and it was always mysterious actually. They got some agreements, but those agreements, it was really no apparent non-normalization theorems that made them have to agree. So now I think we can do it differently by the perspective, it seems to me, I mean, I've just only outlined it, but the perspective that you're saying is that, hey, we should try to integrate out basically the theory near the black hole. And we should think about that as some kind of point-like theory at an inner boundary, that is actually coupled to the whole rest. And however, it's a point-like theory where I do understand some of its internal dynamics. So there's some boundary dynamics there that I can couple to infinity. And if you try to do that, then an important question is, how does it couple to incoming modes? How does it basically, what are the absorption cross-section for incoming modes? And the absorption cross-section, famously, we know what it is that at low frequency, it gives just the area in the low energy. So that really is the full, this is the full geometry, right? And that's what it gives universally for all black holes. But now what's less obvious is that this thing you can actually rewrite. And you can rewrite this in terms of a scale, where you can say, oh, but this thing here actually came now from a scattering process where you had a number of sitting modes that were the S0 that were sort of just sitting there. And then you had some modes that were excited, that sort of came in and were hiding them, that were hitting these guys. Those modes were the L times T. And they basically saying, this is my phase space factors. I have this many modes that can hit this many modes. And they are coupling to each other with a 2D gravitational coupling constant. And then, lo and behold, this is not obvious, these things, they actually agree. So this is sort of the modern, I think a modern interpretation of what Larsen and Mathur were saying is that where we can perhaps say that in effective field theory language, and the L, I would say here, really is my complicated L. You need the full thing with 4 pieces and whatever in order for this to agree for all parameters. So they only did it in the dilute gas regime for a single long string scale. So this thing here, I've not worked it out. I have worked out the numbers, but I've not worked out the logic, as you say, well, so does this really hold up? When you're saying, is this, but I think this is an outline to something that would answer what you were saying, is that here it's saying things that well, I really know what I'm doing. I'm looking, it's flat space gravity. And I know what the gravitons are and whatever, and especially a very low energy, I can find absorption cross sections semi-classically. It's quite unambiguous. And now comes, how can I then repackage that in terms of my Schwarzian type theory? And I'm encouraged by the fact that the L really is the L that we have.
And just one more part of it is that your rules for good holographic renormalization should be derivable from this one, right? Because flat space things are ambiguous.
No, that's fair. No, I see what you're saying. That the various rules that are being used presumably by Sandeep, but also certainly by Kitaev and by the other, that they're probably right, but.
I think Sandeep takes more or less this one.
Yeah.
I think he tries to derive it. Is that fair? Yes.
So this S0 is the structure?
That's the ground state. No, this is the ground state entropy. This is the ground state entropy. So here we're taking the view that we have a bunch of modes coming in one direction, hitting some that were already sitting there. And so these are the phase space factors. And then for that, then you need to find a cross section. So this is basically the cross section. So this is the amplitude squared. Then times some gamma factors. There's a gamma right and a gamma left, which is basically phase space factors. And then the fact that these things actually multiply together to give the area is not obvious. And this is a many parameter agreement. Because there are all these 4 scales and whatever that all appear the right way.
If you wanted to see actually the interaction with Schwarzian degrees of freedom, then you would have to go to higher energies?
No, I think it's the same. So I've only done this in the way, basically, by generalizing.
Coupling
I think it's the same thing, because I think that L times T, I think this is the Schwarzian. So I think that this, so I think that this comes from the Schwarzian. But as I conceded, I have formula and no logic. Some people have only logic and no formula, but.
Could you list some names?
Okay, so when are you turning this one off?